Gate design for legged microrobots at the millimeter scale is a daunting task. Running experiments at the microscale is time-consuming, and there is a lack of accurate dynamic simulators at the millimeter scale. So, how can we solve locomotion tasks at the microscale in a data-efficient way? Our contribution is twofold. First, we introduce a curriculum of increasingly challenging locomotion tasks to validate the parameterization of the controller used in Bayesian optimization as a data-efficient learning approach. Second, we propose a novel approach to efficiently learn locomotion primitives from scratch by converting a contextual policy search problem into a multi-objective optimization task. In our experiments, we used a simulated version of the Microrobot. This millimeter-scale MEMS walker has 6 legs with motors actuating planar pin joint linkages, each with 2 degrees of freedom. For the controller, we chose to use a central pattern generator to reduce the number of parameters. To validate the controller used in Bayesian optimization for microrobot locomotion, we tested a curriculum of increasingly difficult locomotive tasks. We chose to optimize 4 nature-inspired hexapodal gates: dual tripod, ripple, wave, and 4-2. First, we trained our robot to walk in a straight line, with our singular objective being speed. Bayesian optimization consistently converged on a functional gate in 50 iterations. We also used multi-objective optimization in order to optimize gates for both energy efficiency and speed. We found that dual tripod was the most energy efficient gate below 0.6 centimeters per second, at which point ripple becomes the most efficient. We then used contextual Bayesian optimization to train our robot to accomplish more complicated tasks. Here, we trained the walker to adapt to climbing inclines, where we used the inclination as our contextual parameter. As you can see, training was vastly accelerated when comparing the contextual optimization to the normal optimization when tested on a novel incline. We also used a similar process to train the robot to learn to turn to desired trajectories. Once again, training was vastly accelerated when comparing the contextual optimization to the normal optimization when tested on a novel trajectory. Finally, we propose a novel method for learning motor primitives by reformulating the task as a multi-objective optimization where the 2 objectives are the true x-y displacements observed during the previous contextual optimization. This allows us to make full use of the information collected for the contextual case to train a multi-objective model without any additional iterations. We found that this approach substantially boosted model accuracy. As a proof of concept, we demonstrate that our microrobot can navigate a previously unseen maze using our primitives learned in under 250 training iterations. In conclusion, we validated Bayesian optimization as a data-efficient approach for learning locomotion. Although we don't expect the gates learned to be directly transferable, our methodology can be realistically applied to physical robots.